Mathematically, 0.1 plus 0.2 is obviously 0.3. But if you type 0.1 plus 0.2 equals 0.3 inches the Python interpreter, it'll tell you false. So why does Python get it wrong? Or is it even really a mistake? Let's take a look. Computers store data in memory, which you can think of as a continuous space made up of many memory cells. Each cell is made of several bits, and each bit can only hold a 0 or 1. That means all data has to be converted to binary when stored. Here's the catch. We use decimal numbers, but some decimal fractions may repeat when converted to binary. Since memory cells have a limited number of bits, they can only store finite approximations of these fractions, which leads to precision errors. Take 0.1 as an example. To convert a decimal fraction to binary, the most common method is binary result starts from the fractional part. Keep multiplying the fractional part of the decimal by 2. Take the integer part as the next binary digit, and use the remaining fractional part for the next step. Repeat until the fractional part of the decimal becomes 0 or starts repeating. Notice that starting from 0.6, the process starts repeating. From this, we can obtain the binary representation of 0.1. Then we standardize it into binary scientific notation. We can do the same for 0.2 and 0.3, getting their normalized binary representations as well. As mentioned before, memory cells have a limited number of bits, so they can't store infinite repeating binary fractions exactly. They can only store approximations based on the nearest round rule. Let's assume the computer can keep at most 4 fractional bits. For 0.1, the right part larger than 1, so we round up. It gets stored as 1.101 times 2 to the power of negative 4, which is 0.1015625 inches decimal, slightly greater than 0.1. Similarly, 0.2 is stored as 1.101 times 2 to the power of negative 3, which is 0.203125 inches decimal, slightly greater than 0.2. For 0.3, the right part less than 1, just truncate, so it gets stored as 1.0011 times 2 to the power of negative 2, which equals 0.2968875 inches decimal, slightly less than 0.3. All of them have small precision errors. Now, let's explain why, in Python, 0.1 plus 0.2 doesn't exactly equal 0.3. Let's add the actual stored values of 0.1 and 0.2. First, align the exponents, then add the mantises, and finally normalize the result. We get 1.00111 times 2 to the power of negative 2. Since we assume the computer keeps at most 4 fractional bits, we need to round up here, so the final result becomes 1.01 times 2 to the power of negative 2. This equals 0.3125 inches decimal, which is noticeably larger than the true mathematical value of 0.3. As we saw earlier, the stored value of 0.3 is actually slightly less than 0.3. These small rounding errors in opposite directions are exactly why 0.1 plus 0.2 equals 0.3 evaluates to false in Python. In reality, Python's floating point numbers follow the IEEE 754 standard, which keeps 52 bits after the binary point far more precise than our simplified 4-bit example. If you have the patience to repeat the same process step by step, you'll end up with the exact same result in the end. I don't have that much patience, so let's directly take a look at how Python actually stores the values of them. It's very simple, we just need to ask Python to display more decimal places. You'll notice that the stored values of 0.1 and 0.2, as well as 0.1 plus 0.2, are slightly larger than their true mathematical values, while the stored value of 0.3 is slightly smaller, just like in our 4-bit fractional example.